Exponentiation is the process of repeated multiplication. We've already explored multiplication as repeated addition, but we can multiply over and over again. We're going to write our power as b raised to the nth power. The n is written above the line. We call that a superscript, written above. B is going to be our base. We're going to multiply b by itself a certain number of times, n times. N is our exponent, x to the fourth power. X is the base, 4 is the exponent, and we're showing that we're multiplying x times itself 4 times. Here we have 2 raised to the third power. That's 2 times 2 times 2. 2 times 2 times 2, that's going to be 8. So sometimes we know what it is we're multiplying together, the 2's, 2 times 2 times 2. Sometimes we don't, just some x's, and we can't go any farther with that one until we find out what x is equal to. So what if our exponent is equal to 1? How many x's? Only one of them. So we don't need all of these. X to the first power is equal to itself. 2 raised to the first power is equal to itself. 1,000 raised to the first power is equal to itself. That's the one exponent property. Product of powers property says that if we have two powers that we need to multiply together, if they have the same base, we can add the exponents. What if our base is x? There's 2 of them there. There's 3 of them there. And we want to multiply those together. Well, we've got x times x, that's x squared. And we're going to multiply that by x to the third power. How many do we have? Well, there's 2 of them there. There's 3 of them there. All told, we're multiplying 5 x's together. So we have x squared and we have x cubed, which is x to the fifth. We have our power of a power property. If we have a power raised to an exponent, we can multiply those two exponents together. Maybe we have x squared, and that whole thing is used as a factor 3 times. Got 3 of them. There are 6 of those x's. Now we have our power of a product property. If I have two numbers multiplied together and then raised to a power, then I have the first one to that power times the second one to that power. What if we have, for example, 2 times 5 raised to the third power? 2 times 5, another one just like it, and another one just like it. 2 times 5 times 2 times 5 times 2 times 5. Now we can use our commutative property of multiplication, which means if we're multiplying all the way across, we can multiply in any order and come up with the same answer. So we can bring all of our 2's to the front and all of our 5's to the back. We have a bunch of 2's multiplied together. Looks like there's 3 of them. And we have a bunch of 5's multiplied together. Looks like there's 3 of them. That's 1,000. Now we have our quotient of powers property. If we have a fraction that has a power in the numerator and a power in the denominator, the bases have to be the same. I can subtract the exponents, and here's how that goes. Suppose I have 5 to the 7th power divided by 5 to the 3rd power. If it's multiplication all the way across, I can divide out things that match exactly. I have nothing left in the denominator. If you have nothing left, there's always that invisible times 1. So how many do we have left in the numerator? Well, there were 7, and we divided out 3 of them. So we've got 5, we've got 4 of those left up there, and a 1 in the denominator. So how did we get those 4 left in the numerator? Well, there were 7, and we divided out 3 of them, and there were 4 remaining. Let's do another one. About 3 to the 4th times 3 to the 8th in the numerator, and 3 to the 7th in the denominator. Well, in the numerator, we can use our multiplication property. 3 raised to the 4 plus 8 up there, and 3 raised to the 7th down here. Let's see, 4 plus 8 is going to be 12, and we can subtract 12 minus 7, which is 3 to the 5th. We have the power of a quotient property. If you have a fraction that's raised to a power, you can apply that exponent separately to the numerator and the denominator. Here's a fraction, and I want to raise that to the power of 5. One big fraction. We multiply all the way across the numerator, and we multiply all the way across the denominator. So in our numerator, we have a bunch of 2's. How many of them? 5. In our denominator, we have a bunch of 3's. How many of them? 5. And we could calculate that out. Okay, next up is the zero exponent property. And it goes like this. What if I have 5 raised to the 7th divided by itself? Well, we know that anything divided by itself is 1, right? Well, let's multiply this out. Here we have 7 of those, and just the same in the denominator. And since it's multiplication all the way across, we can divide these out pairwise. Our base was 5, and there were 7 in the numerator, and there were 7 in the denominator. 5 raised to the 0 power. And this would have worked if the base was anything. Base didn't have to be 5. Nothing magical about that. Base could have been x. Base could have been 17. Base could have been anything. If there's the same number of them in the numerator and in the denominator, you're going to get a 0 exponent. So anything raised to the 0 power is equal to 1. So here's the negative exponent property. If you have any base raised to a negative number, what we're going to do is we're going to change the negative exponent to a positive exponent and move the whole kit and caboodle into the denominator. It looks like this. Let's go 3 to the 5th divided by 3 to the 7th, and 7 of them down below. And they'll divide out pairwise. And remember, there's always that invisible 1 when you're multiplying. This is 1 over 3 squared. Well, where did that 1 over 3 squared come from? Let's use our quotient property. Our quotient property said 3 to the 5th divided by 3 to the 7th is equal to 3 to the 5 minus 7, which is 3 to the negative 2. 5 minus 7 is negative 2. So 3 to the negative 2 that we see down here is the same as 1 over 3 to the 2 up there. So if you have a negative exponent, change the negative to positive and put your whole power down into the denominator. What if your exponent itself is in the denominator? Can we have a fractional exponent? Yes, we can. And here's how we're going to do that. Suppose we want to write the square root of x as x raised to some exponent. I'm going to call that k. Don't know yet what it is, but we want to find a k such that x raised to the k is equal to the square root of x. From our definition of square root, we know that y is a square root of x if y squared is equal to x. That was our definition of square root. So we want to write y is equal to x to some power. We want to show that as the square root of x, and that square root of x squared is equal to x. Well, let's hit this thing with our power of a power property and go x raised to the power of k times 2, or 2 times k, either way, is equal to x. And there's always that invisible power of 1 there. So x raised to the 2 times k is equal to x raised to the first. Now, if the bases are the same, then the exponents must be equal. So 2k is equal to 1. Then k must be equal to 1/2. So that's going to be our k. So we can write the square root of x is equal to x raised to the 1/2 power. That's the value of k that we just found. If that's the square root of x, then we should be able to square that. We should be able to square x to the 1/2. Is that equal to x? Well, that's x raised to the 1/2 times 2. Is that equal to x? Yeah, it sure is. Okay, so that's how we're going to annotate square roots. We're going to say that a number raised to the 1/2 power is the square root of that number. And we can use the same logic. We can say that the third root of a number, let's use a difference, use w this time. We can write that as the base raised to the 1/3 power. We can generalize that. We can use the same logic. We can say that the nth root of a number, let's use p this time, is equal to p raised to the 1 over n power. That'll be the nth root. The fractional exponent property. If we have a base raised to a power that is a fraction, we can write that as the nth root, n is the same as the denominator, of the base raised to the numerator. X raised to the m over n is equal to x raised to the power of m times 1 over n. X to the m can be our new base. And we just said that 1 over n power is the same as the nth root. And that's our property. Let's try it with real numbers. How about 9 raised to the 3 halves power? That'll be 9 raised to the power of 3 times a half, which is 9 raised to the 3 to the 1 half. So that'll be the square root of 9 to the third. How much is 9 to the third? 729. Square root of 729. Of course, now we have to ask what's the square root of that? Turns out to be 27. We can do it in a different order too, because 9 to the 3 halves is also equal to 9 to the 1 half times 3. And that'll make things a little bit quicker, because 9 to the 1 half, that's easy enough. That's 3 to the third. And we get the same answer, which is nice. Okay, so those are our rules of exponents, the properties of exponents. So if you like this video and you want to see more of my math lessons, you can check my playlist right there. And if you want to see the new ones when they come out, go ahead and smack me in the face down there and subscribe to my channel. Thank you very much.